So the Rio Grande, guys, is a very important, crucial aspect of our ecosystem, as you guys know. Without the Rio Grande, then of course Laredo would not exist, because we need water, right? This is the source of our drinking water. And again, in the background, that concrete slab in the background, that is the Pico water treatment plant, and that is up on Mines Road, and it basically collects the water for us to use, and it cleanses it. Hi guys, Mrs. Kelly here again. I'm on the Rio Grande, and I can't assure you that if you join our LEAPS program that you're going to be here on the Rio Grande like I am, but I can assure you that there's valuable research, valuable data to be collected. For example, in my background here, we've got some cliff swallows, or perhaps some cave swallowbirds that are yet to come to Laredo, because right now it's still in the winter time, but we should be getting them in the next couple of weeks, and that would be a great source of scientific data to collect. I don't think anyone right now is collecting data on these, but again, just another research opportunity. So again, signing off guys, thank you very much. Hi guys, Miss Kelly again here. So another research opportunity that you could have here at Laredo College is on birds. There's a wide diversity of birds here in Laredo. As you can see here in the background, right here in that tree, there is a flock of about maybe 10 black vultures. So, and that's just one of the species that we have around town. So again, another research opportunity for the LEAPS program if you're interested in birds. My name is Mrs. Kelly. Thank you. So today's lab is on roots, and as you all know, that roots, guys, are a major component of plants, like this jalapeno here. And roots absorb nutrients, absorb water, and without a good root system, the plant will not survive. So we have two different types of root systems. We have tap roots, and we also have fibrous root systems. And then there's other ones also, like adventitious roots, but again, they all serve the same purpose: to absorb nutrients, absorb water, and also to anchor the plant to the soil. And again, this is the main purpose of today's lab that the students are doing. They're working on the garden, they're planting vegetables, they're getting it ready, making sure they have a good root system and a good healthy soil.
We're out.
We're out.
Hello everyone. Okay, my name is Michael Meng, and I'm a chemistry instructor here and teaching chemistry. Okay, I'm so happy today to have the opportunity to present one of my research. Okay, and thanks to the LEAPS program that I had the opportunity to do the research with the undergraduate student involved. Okay, and my research, I got my PhD in chemistry about 10 years ago. Okay, so the research I'm doing right now is called photocatalyst. Photocatalyst. Okay, so this word actually has two important components. The first component is photo. So that means our experiments in the research is going to use the light as the power to initiate, to start the chemical reaction. Okay, so we can use the sunlight, or actually in our science lab, chemistry lab, we can use the light as the power, okay, to start the reaction. And with the second component, catalyst. Okay, so you might never heard of a catalyst. So this catalyst means some of the chemicals will be able to speed up the chemical reaction, because what the research I'm doing, the reaction might take very long, maybe a month, maybe a year, very long. But after we add the catalyst, okay, so sometimes the reaction gonna take only a few hours, then we can do the research. Okay, so that is the catalyst about my research. Okay, and my research is gonna associate to two branches of the chemistry. And the first one is we're going to use the photocatalyst to do the environmental chemistry. For example, we want have a very clean environment. Nobody wants to drink some dirty waters. Okay, well, what if our drinking water, for example, contaminated by some organic pollutants? Okay, what are we gonna do? Okay, so that's one of my research, trying to use the photocatalyst to get rid of all the organic contamination in our drinking water. Okay, so that's the first application of my research. And the second part of my research is trying to use the same photocatalyst to use in the energy chemistry. Okay. For example, we are using a lot of gasoline to drive the car. Okay, so what if 100 years or 200 years later, what if our Earth kind of run off of the gasoline, so we don't have any fuels anymore? So what we do? Okay, so the second research we're doing right now is trying to use the photocatalyst, the new chemicals we synthesize in our science lab, okay, trying to produce more new renewable energy sources, okay, other than the gasoline. Okay, so that's the two major branches of my research could be. Okay, so today I'm going to show everybody two demos about the major experiment we're going to do the research. Just give you a heads up, give you an overview, so how our research, how our experiment looks like. Okay. So the first one, remember we're going to solve some environmental problem. Okay. So in the science lab, okay, at the very beginning, we're going to use a lot of chemistry technique to do the synthesize. Okay, we're trying to synthesize, for example, the photocatalyst. Okay, so here I have something to want to show everybody. Okay, the new chemicals, the new photocatalyst synthesized by my current students, the LEAPS program students. Okay, so that's how my sample looks like. Okay, so now I'm gonna put it on paper. You're gonna see what our chemicals looks like. Okay, see, it looks like a white powder. Okay, and they do have some chemicals. So if you are interested in my research, come to my lab. Okay, I will show you what the name of these chemicals and how we're gonna synthesize it. Okay, so that's our photocatalyst. Okay, so first demo experiment I want to show everybody is this is the solution that we made in our lab. Okay, so see, actually that's what the initial looks like. See, it is very pink color. So we already put a lot of organic chemicals in the water. Okay, so zooming or mimicking, that is the dirty water. Our drinking water actually contaminated by a lot of organic compound. Okay, so we're gonna use our photocatalyst to get rid of those organic pollutants. Okay, so what we will do is we're gonna pour our dirty water, okay, with a lot of color inside, means there's a lot of organic compound inside. Okay, so what we're gonna do is pour our solution, dirty water, in the beaker. Okay, you're gonna see, okay, it's very dirty. Okay, and then we're going to pour our synthesized photocatalyst into the dirty water. So that dirty water can be later on it will be cleaned by our photocatalyst. Okay, with the help of the sunlight. Okay, so we of course in our lab we don't have the sunlight, but we are using some other light sources. Okay, zooming. Okay, here's the sunlight, okay, shining on our dirty water. Okay, with the photocatalyst inside. Okay. We will let it stay. Okay, we don't have enough time to show the whole process. Okay, so now after 3 hours, 4 hours, after a while, okay, so all the organic pollutants are going to totally decompose. Okay, so what we're going to see is the color of our dirty water going to be lighter. Okay, so I will not show the whole process, but that is what the solution after about 4 hours looks like. See, compared to what it looks like before. Okay, so now the color is much lighter. Okay, so it means a lot of organic compound has been decomposed. Okay, so if given enough time, okay, like 10 hours, okay, we will have our dirty solution. Okay, looks like exactly like water. Okay, if given enough time. Okay, so by that we can successfully use our synthesized photocatalyst to get rid of, to remove all the organic compound in our drinking water to give our clean environment. Okay, so that's the first research I have. So remember the photocatalyst, I'll show you, so it looks like a white powder, and how did we made it? Okay, so that's something I want to introduce to everybody. Okay, so one of the method we're going to make this photocatalyst is called a thermal method. Okay, so we have the oven, okay, very high temperature. Normally temperature will goes up to as high as like 1,200 degrees Celsius. Okay, so at that high temperature, we'll be able to successfully prepare to synthesize our photocatalyst. Okay, some may be white powder, some may be green, some may be yellow. So it depends. So here's our oven. So even it is small, but temperature can go as high as 1,200 degrees Celsius. And the second one I want to show is called spectrometer, because we are working on the photos. Okay, so the optical property of our sample is very important. So we're going to use our spectrometer to characterize the optical property of our synthesized photocatalyst to understand what is the structure, what is the property of our chemicals. Okay? And the third one I want to show everybody is called IR spectrometer. So that technique will allow to understand more about the structure of our new synthesized photocatalyst. Okay, to understand their structure, how the structure associated to the chemistry properties. Okay? And the last one I want to show is the microwave. It looks like similar to the microwave that we use every day in our kitchen, but that one is specially designed for the research to do the synthesize. So it's called a microwave assistant thermal method. Okay, because using a microwave, not only the synthesize, okay, going to take a very short time. Okay, maybe like a half or even 1/10 of time of the time required to synthesize our photocatalyst.
Welcome to the world of physics. In the study of physics, we learn electricity, and there are two types of electricity. We have electrostatics and current electricity. We focus today on electrostatics, which is a branch of physics that deals with stationary or resting charges. One of the fundamental laws of electrostatics is like charges repel and unlike charges attract. I'm going to show you a demonstration over there to demonstrate attraction and repulsion. I have a balloon in my right hand and a pipette of water over here. To demonstrate the effect, let's see when there is no charges on the balloon yet. So I'm gonna let the water drop here next to the balloon and let's see what happens. So you observe that the water is going directly downward because of gravity. But if I'm going to rub the balloon here, so I'm scraping electrons on my shirt, transferring them to the balloon. So let's see what happens now. Okay, you see that the water is attracted to the balloon. Okay, that's attraction. Let's consider here repulsion. So this is electroscope. Okay, so when I'm going to rub this glass here and put it on top of there, then you will see that the leaves of the electroscope will repel each other. Okay. There you go. That's repulsion. This is a Van de Graaff generator to see also the effect of charges on a bigger scale. So we have here serial. Let's see if there is attraction or repulsion here. So let's put it over here. That means charges, if this one will show reaction, which is either attraction or repulsion, then we can say that it reacts also to non-metallic objects. To show that there is metallic, we're going to show this one and this one later. Okay, so you turn it on and see the reactions. Okay. What about for metallic objects, such as these fall pans? Okay, let's start with something light. What about if we have something heavier? Can it push it out? When we study electricity, we also know that we can isolate charges. So if we have this plate here, metal plate, is positively charged by connecting to the positive terminal of the battery, then this will become positively charged. And the other side here is also a metal plate, and if we connect it to the negative terminal of the battery, it is also charged negatively. There is an electric field that goes from positive and terminates to the negative of this plate. We are not going to map the electric field directly, but we're going to map the equipotential lines and the equipment that we'll be using later. After we map these equipotential lines, we are going to draw your electric field lines, and they are always perpendicular to each other. The electric field lines will come out perpendicular from the positive plate, perpendicular with the equipotential lines, and also perpendicular as they come into the negative plate. So this is what we're going to do in the experiment, or in the activity we're going to be doing in a little bit. We're going to map the equipotential lines. The equipotential lines come from the word equi, means equal, potential means voltage. So the voltages on any of these points will be equal, and when you move an electron, any of these points, you don't need to do work in moving the electron. However, if you move the electron or proton, as the case may be, if you go from this point to that point, you're going to do work in moving the electron or the proton. So along these lines, any position here should demonstrate a zero or null voltage, because there's no work done in here. So to map this out, we're going to use an equipment called electric field mapping, and after that we're going to draw the electric field based on the equipotential lines.
Okay.
You're gonna color code later, okay? You're gonna do, yeah, I'm gonna do one, and you're gonna do one of this, and then you're gonna do two, and then you're gonna draw your electric field, okay? So you're gonna color the equipotential line blue, and the electric field lines positive.
Alright, so we can do one.
Yeah, I'm gonna demonstrate like maybe 3, 4, 5 dots here. I'm gonna draw one line, and you're gonna do this one here, and then this one. So you have three.
Okay,
Yeah, so it's gonna be quick, okay?
Yeah.
So you're gonna do one first. No, I'm gonna do one first, and then you're gonna do the second one, and maybe the third one for you, or whatever you decide. Okay, so we're gonna begin in
2, 1.
So this is our setup for the electric field mapping. So we are going to map, as I mentioned earlier, the equipotential lines. And we have here the potential or voltage supply, and then we have the electric field mapping apparatus, and this is how to determine how much voltage is going to be measured. So using the null voltage is going to be over here, it's going to display 0. So with this equipotential line field 2, I'm going to be able to find a 0 in there. If you see, if I move this on this side, it fluctuates to this side. If I move the other side, it fluctuates the other end. So we're going to find the 0 so that we can determine the equipotential line. So if you look at this, it's going to display 0, and you're going to mark here where in the galvanometer displays 0. That's one of the points, and then find another point that will display 0. Another one over here. And to have symmetry, we have to do it also on the other side. And also the far end on that side. So if you're done that, you come up with a generalization that this is supposed to be a connected line. All those dots. So this is one equipotential line. Meaning when you move a charge here at any point, you don't need to do work. That's why it's going to give you a 0 voltage, or the equipotential is the same. I have here 2 of my students to demonstrate how to do other equipotential line in the next few seconds. Okay, good. We're going to be having electric field lines later. These are equipotential lines, so I want you to color this with blue, those lines. Okay, we're going to use this color of the Sharpie red, and we know the electric field will go from positive to negative of these two plates, and as they come out they need to be perpendicular from the positive plate go to the negative plate, and as it touches this they need to be perpendicular as well. Need to be perpendicular. You don't have to put perpendicular, just to emphasize that they are perpendicular, and you have to write an arrow anywhere to determine that it goes from positive to negative. You can put it here, or you can put it there, or you put anywhere along the line. So I want you to draw more lines, electric field lines, on this side and at the other side. At this side is going to be a little curve because they need to be perpendicular. Thank you. So you can see here that they are visual representation of electric field. We cannot see them, but through this graph that you have created or figure, you can visualize that the electric field goes from positive to negative terminal of metallic plates. Okay, we're going to turn this off, and then I'm going to show it to you a more visible and practical applications of electric field. So I have here with me a plasma ball, and you can see that the center represents the positive, so you have your lines made up of blue color where they're coming out in here, and they are receptive both to, electric field are receptive both to touch and also to sound. So if I touch this one, you can see that they react with it. Okay, try it, Brian. Put more fingers in it. Okay. Thank you. And come over here, Javi. And I want you to clap, produce sound, so see if it gives you a reaction. Okay, so you have a visual representation of what electric fields are. The lesson today is about conservation of linear momentum and at the same time conservation of mechanical energy. And the equipment that will summarize these two is called the ballistic pendulum. So the ballistic pendulum will tell you that when it is released, then they have a mass and velocity of two situations. So can you scroll down for the next slide? Okay, so when you fire the ball over here, you have a velocity initial of the ball, while this pendulum here is going to be zero velocity. They have their own masses, so they have their own momentum. The initial momentum of this ball will be converted or transferred to the momentum of the pendulum. And you can see that it's going to be a conservation of linear momentum over here, alongside with the conservation of energy. When the object goes from this height to a certain elevation, you can calculate the change of potential to kinetic or the other way around. So to do the mechanics of this, just scroll to the next slide. So to show conservation here, we have to analyze before and after momentum of this ballistic pendulum. So the mass of the ball here with initial velocity, then we have here the pendulum is a mass, but the velocity is going to be 0 because it's at rest to begin with. When this ball hits this one, then we have the after process. So when the ball is inside, it's going to be called inelastic collision because they are going together. So the mass and the velocity combined of these two is going to be equal to the momentum, mass and velocity before. So when you calculate the velocity over here through your conservation of energy, which is your kinetic energy converted to potential energy, then you will be able to determine the initial velocity of the ball over here, which is the velocity Vxo. Can you please show this slide, please? Okay, to underscore what I've said, we have here conservation momentum, so momentum before equals momentum after. Using equation now, so we have mass of the ball, initial velocity of the ball is equal to the mass of the ball and the mass of the pendulum combined. They have their own final velocity. So if you combine it with kinetic energy after collision and potential energy over here, it will give you 1/2 mass times mass of the ball, mass of the pendulum combined, and this will be the initial velocity of the ball, and that will be the change in potential energy of the combination of the ball and the pendulum. So once you determine this velocity here, you're going to have, using this equation, the m over m here cancel out, then the 2 you multiply 2 on both sides. So it's going to be cancel this one, then it's going to be 2gh, and then you square root both sides, so we have here v is equal to the square root of 2gh. You plug in that to the original equation, we come up with this equation. That's what we're going to need to determine the initial velocity of the projectile in the equipment that's provided over there. Okay, we're going to cock the ball here. Once you cock it, we're going to measure the initial height, or we call it h1. So it's going to be the height from the top of the platform to the red mark over here. You're going to measure that in centimeters, and then you convert that to meters. Come over here and read it for me, please. Okay, Ruben, read up to here.
Up to on the red line. We have 7 centimeters and a half. So
That's h1.
so how much is it? It'll be 0.07 meters.
Okay. Once you have that, you're going to let go of the ball by pressing this one, depress this, and this one will go together over here. Okay, measure this height from here to the red mark over here. That's going to be your h2. Convert your centimeters to meters.
Now we're going to get it.
Okay, you're going to calculate your h, which is the difference between h2 and h1. Okay, so with one trial, we were able to determine that there is a initial velocity of the ball of 2.14 meters per second. Usually in the study of science or in physics, we have to do more trials to confirm the results. So make sure that you do also more trials so that you will have more conclusive results. Okay, in this lab setup we will be doing today is going to be about change in temperature, so it's introduction to thermodynamics. So I want you guys to put this boiling water on this cup over here, and this side here is going to be a cold water or ice water. After that, you're going to put this in, and let's see if the change in temperature can cause this one to rotate or spin, which we call it an energy transfer or energy conservation. Okay, make sure that this one is at the bottom first. Flip the switch here, bottom. Yeah, okay, and then you're gonna put them here. Wait for like a minute, and you're gonna flip the switch to up, bottom, okay? And let's see what happens. So as you can observe here, there is a change in temperature of the hot water and the cold water. The change in temperature here is converted into mechanical form of energy here. Now I want you to take this out from here, put it here, and it keeps spinning due to angular momentum. But eventually it will come to stop. So this one we're going to have another setup to be able to realize that these two are related, but it's going to be a different way of looking at it because you will not have a cold water. So it's going to be a hot water over here and the cold is going to be the air over here. So the air is cooler, the water is hotter, there is still a change in temperature. Let's see if the Stirling engine is going to be work as well, or it's going to run. Okay, I want you to transfer this hot water over there in the cup. Wait for like a minute. It didn't stop right away because of inertia. Now that it's spinning, it keeps spinning. Okay, I want you to put this one at the bottom, and the source of the heat is no longer there, but it's still rotating. It is rotating because it has what we call angular inertia and angular momentum. It will eventually stop because the angular momentum is going to be conserved, because you start at none, it will end at none as well. Okay, this topic is going to be Paradise electromagnetic induction. As you can see here, to demonstrate that, we have coil of wire, which we call it solenoid. When current passes through it, the result is magnetic field is produced surrounding the coil. We are going to replicate a windmill. So imagine that this is the propeller, and then this side is another. This propeller has 3 prongs. And when the wind blows on it, what do you expect will happen? It will turn on. So instead of blowing it, you're going to crank this. Okay, so let's say this one. You do it slowly. What do you observe with the amount of light that's going to be delivered there? Okay, less. Okay, do it faster. So the speed has something to do with the amount of electricity generated. Okay, so this one here are 2 identical generators, or Genicon. So this one will demonstrate that a generator is similar to a motor. So a generator is defined as a device that converts mechanical energy to electrical energy, while a motor is fed with electricity and it will produce a mechanical energy. So I want you to use this device. Come over here. So if this one will be mechanical and this one will produce electrical, so this is a generator, while this one it's going to be fed with electricity and it will produce a mechanical energy. Okay, can you do it? Okay, so can you reverse it? Okay, so what is your conclusion here? How are generator and motor related to each other?
One produces the charge and the other one is consuming it, so he can both.
Okay, so you're saying that this one here is using mechanical energy to produce electrical, while this one is electrical and the output is mechanical. So basically you're saying they're similar devices, very good, and with their input and output flipped.